My name's Mark Morgan, and I'm the department head and professor at the University of Tennessee. And my main area of interest is hygienic design of processing equipment. That's something I do aside from the department head job to keep me engaged and interested. And so I'm here today to just talk to you a little bit about hygienic design of equipment, introduce the organization EHEDG or EHEDG if you haven't heard of it, because they're quickly becoming a global organization for the promotion of hygienic design. So we'll go through a few examples. I've got some pictures of equipment actually on the floor, and I've been walking around asking people about their program on hygienic design. So let's get started. So a little background, first few slides on EHEDG and where you can find more information, because in this 1 hour I can't do everything I'd like to talk about hygienic design. So I want to introduce this organization, and you can go to their website, and we have training courses, etc. So the EHEDG, European Hygienic Engineering and Design Group, is quickly becoming a global advocate for hygienic design. They now have regional sections in different parts of the world, but they mainly work on writing guidelines and offering training courses on hygienic design. We also have some test methods that we can use to validate hygienic design of equipment. Really screening tests to look for areas that are difficult to clean in equipment. Can you all hear me okay? Okay. And so I'll show you a little bit of that later as well. But the main thing is really to promote hygienic and disseminate hygienic design of equipment. So I see that I can't really even point at anything, so yeah, you'll have to just bear with me on that. What I wanted to point out here is that they do have subcommittees on regional development, regional subcommittee development, product portfolio, which includes their design criteria, and different working groups on different pieces of equipment like valves and pumps, and they're always looking for volunteers to help out with those guidelines on the best design for different types of equipment. And they also have a communications group. The working group clusters, here's an example of some of them: equipment and components that the people are working on, principles of design, processing and utilities, even services, as well as the training and education group. And I'm a member of both the principles and the training and education subgroups, or working groups. There's and you can see there's lots of volunteer members of EHEDG that are working towards hygienic and promoting hygienic design. This is a list of some of the regional sections that have been created by EHEDG. So it's not only, even though Europe is the first word in the name, European, they're going global. They now have regional sections in Taiwan, Thailand, and Mexico, and they're really interested in having a regional section here in the U.S. I've told them I'm not the one to lead that group, but I will help find people that are willing to participate in that and have more discussions about hygienic design of equipment, especially here in the U.S. and those kind of activities. So they do have this. They do have 7 authorized test institutes around the world, and these test institutes, I'll explain later, handle their certification program. If you're familiar with 3A and all the great things 3A has done for the dairy industry, EHEDG is trying to do that as well for all kinds of processing, either whether it's open equipment or closed equipment processing. And so as the U.S. Authorized Test Institute, I will evaluate hygienic design of components or pieces of equipment, and if it's a closed piece of equipment, we can test it to demonstrate that it is easily cleanable, and they have a certification program for that. I'll explain a little later. So the scope of the training courses, just briefly, we just had our last training course last week at the University of Tennessee in Knoxville, and we cover all kinds of things from hazards, hygienic design criteria, materials of construction, welding, pumps and seals, even facility design, the building layout and design. We talk about those things as well. So there's lots of components to it. We invite anyone from the industry, but in particular equipment manufacturers and processors. End users are really the ones that are driving hygienic design. They're the ones requiring more hygienic design. And when I say hygienic design, I'm talking about cleanable design, something that is easily cleanable. It's not really hygienic until you've cleaned and disinfected it. So the design is really something that's easily cleanable. And that's as simple as that. That's what we're talking about here, is something that's easily cleanable. So just to back up and talk about, why is it important? Well, we've all seen different recalls and hazards that occur in the industry. This is one that I'm sure everybody here is familiar with, that was linked to equipment, right? The improper use of equipment and how that contributed to an outbreak of listeria. And so packaging equipment, cold storage equipment, the design of that equipment and its use can significantly impact the safety of the product. This is a more recent one, and unfortunately, Bluebell suffered from this, but they're back online now, up and running. And this, again, was targeted towards equipment, and in particular, equipment that showed some contamination on a non-product area, but over time ended up on the product surface and contaminated the ice cream. And so if it's an open processing equipment where the product is exposed to the environment, then I think the whole equipment needs to be considered for hygienic design improvements. So some of the criteria that we'll talk about are in what is a free document, Document 8 from EHEDG, on their website. And it talks about things all the way from materials to different hygienic design criteria. And I will highlight some of these in the short time that we have here this afternoon to point out some things that we could do to improve the cleanability or safety of some equipment. So I wanted to first back up and talk about some of the definitions so that we're all clear on what kinds of equipment I'm talking about. Open processes or open equipment is something where the product contact surface is exposed to the environment. Lots of it right out here in this hall because it's a lot of meat processing or bakery type processing equipment, conveyors that are open and exposed. Closed equipment would be things like pumps and valves and inline sensors where the product is totally enclosed inside that equipment and it's easily CIP cleanable, hopefully. EHEDG's classification of hygienic equipment class 1 is designed for in-place cleaning. So it could be a conveyor system that has a CIP system built on it, and it would be CIP cleaned without any dismantling. So you can imagine how hygienic that design must be if you can clean everything without dismantling the equipment. That's easier for closed equipment, and that's mainly the target for class 1, but we are certifying some equipment that is open as class 1 as well. The hygienic class 2 equipment is simply stuff that machines that have something disassembled for cleaning. So if you're taking the knives out of a slicer or opening up a drainage channel or something like that, anything that you have to open or dismantle for cleaning, then that would be in our category class 2. Just some definitions. So if we're looking at the machine areas, what I want to point out is that there are different definitions of product contact and non-product contact. And I realize that when you're thinking about hygienic design of all these areas, product contact, non-product contact, you really have to look at a risk assessment, right? What is the risk that my product is going to get contaminated from something on that piece of equipment? If it's very near the bottom of the equipment, the feet or the floor, maybe the risk is low. But if it's near the top or if it's above, like in the picture on the right, anything above that open process could be considered product contact because something dripping down could get into your product. And we've seen that happen in industry and cause recalls. So really the design and the risk assessment tells you what level of hygiene you need in your equipment. But for certification processes or certification aspects, we really look at everything as being a food contact surface, especially for open equipment. Closed equipment, we're really looking at the inside of the equipment. But for open equipment, we're looking at all surfaces. And there's lots of equipment out here that has areas that could be improved. So general recommendations for hygienic design. Drainability. Drainability is a key component of hygienic design. You want to make sure that all the water can drain out or off of your equipment. If there's no water present, then the microorganisms won't be able to grow and multiply. And it really takes that growth and multiplication to cause a foodborne outbreak. And so that's an important part. Sharp corners make it easier to clean. We recommend 3 millimeter radius or greater. Things that slope away from the product, the direct product area, make water and soil flow away from that. No overlapping joints. Metal-to-metal joints are a problem because they will suck water in and bacteria, and that'll be a harborage site that'll continually could cross-contaminate your product. Continuous welding. We'd like to see everything continuously welded. We know that you have to have some components that are easily disassembled, so you have fasteners and joints. I'll talk about that, ways to do that. But we'd like to see things just continuously welded if possible. And if you're going to weld them, make sure the weld is continuous. Don't cut corners and just spot weld, because then you've got a gap between those welds that are going to harbor soil. So just some examples. In welding, if you're welding a vessel, we prefer you don't weld right in the corner, because that corner is the most difficult spot to clean, right? The surface of the material is such that it's going to be easy to clean with a smooth surface, but in those corners, not so much. So welding away from there is a key aspect of hygienic design. Back to the dismountable joints. So we want these areas to be fully drainable, fully sealed. If there's any metal-to-metal contact, we use an elastomer. If you're using an elastomer on a bolt, we'd like you to have controlled compression. So if somebody cranks that bolt all the way down, it doesn't just squeeze the elastomer out and then create a crevice. And ideally, the fastener should be on the non-product contact side, if possible. So here's 3 examples, and you can find these all over the place in this show. Socket head screws, the farthest one on the right. A lot of people want to use socket head screws on bolts on their equipment, and they're nice and smooth to the surface, flush with the surface. But how in the world do you clean the head of that socket? When material gets in there, you can't get it out. Of course you can with a high pressure lance, and then you're just blowing it everywhere, right? How will you ever drain that? How will that ever dry? If you want the equipment to be drainable and dry, how is that ever going to dry? That socket head is going to be filled with a pool of water. Bacteria in there are going to multiply, and they're always going to be hanging around your equipment. Here's just some pictures. Here's a picture where you've got some bolts in the product area, some bolts missing in the product area, and just poor hygienic design. Walking around the show, here's one where there's a socket head screw right in a conveyor area, and you can see the Play-Doh or the simulated food products sticking right on the crevice around that socket head bolt, right here at the show. Does that fastener have to be there? Does it have to be in that location? How do you clean that, right? Here's another one, and it's socket head screws right on the top of a conveyor system. Very difficult to clean, not drainable. Is that necessary? I mean, if those parts need to be removed, then let's put something there that is easily removed or is at least hygienic. How do we do it? Well, here's one solution to get rid of socket head screws. And if that's one thing that you walk out of here with, I would be happy today. Domed head nuts or domed head bolts is one good example. And I did find some good examples here in the show as well. Machinery and conveyors that have these kind of fasteners on them. And they use a gasketed washer underneath. And notice that gasketed washer on the left has a metal center and then an elastomer on the outer edge. So when you tighten that nut or that bolt, it squeezes the elastomer, it seals right at the outer edge, and it doesn't suck any material underneath the bolt head. which is the source of possible source of contamination. That's where the microorganisms and the water are going to be sucked in. So that's a nice example of a nice seal. If you can, get those bolts out of the product area. Put them on the backside. Put studs on the backside of the product. And so it's totally underneath, out of the product area, and you don't have any fastener in the area. Just one example. Welding, I mean, I've seen a lot of good examples of welds. People polish welds. We just want to make sure that any welds in the equipment are free of edges, free of cracks, no porosity, just good treated welds. And we've got a lot of materials on welds, but I can't go into it all here today. I mentioned drainability. So drainability of closed equipment as well as open equipment. If we're talking about pumps and valves, you know, that you may have a very hygienically designed piece of equipment, but if you mount it such that it's not drainable, then it's always going to have water in it. There's always going to be a potential for organisms to grow in that water. And not only that, if it's always wet, what happens to the passivation layer on the stainless? It disappears. If that material can't dry out and see air, the passivation layer will disappear and you will see corrosion on that stainless steel surface. So we want them to be self-draining or drainable if possible. We don't want any horizontal surfaces if we can avoid it. Surfaces should always slope away, and drainage of condensates are also an issue. So it's not impossible to make things drainable. You know, here's a centrifugal pump, which you never see, hardly ever, with the outlet at the bottom. 90% of what I see are centrifugal pumps with the outlet at the top, right? How do you drain that? Does somebody actually come by and open that cover and drain that pump? I doubt it. It sits there half full of water, half whenever it's not in production, right? So here's a good example of a good design I found out here at the show. Centrifugal pump with the outlet down, drainable. Here's another example of centrifugal pump where it can be drained. Here the outlet is pointing up, but they have a drain valve at the bottom. Now that's one way to do it, but that drain valve also has to be clean, so it has to be open during CIP to flush it out. It may, depending on how the design is made, create a dead area, and we don't want to see that either. We don't want to see a dead area where product is stagnant the whole time you're processing. It fills up at the beginning and the product just sits there in that drain valve. But that's another example. If you do it right, you can minimize that concern. Positive displacement pumps. You know, how many do you see in this direction? Very few. Very few do you see that are drainable like this. And all of the literature shows a positive displacement pump with the inlet coming one way and the outlet going the other, right? Horizontal. And so the bottom half of that pump, if it's horizontal, is filled with water, product, whatever, cleaning solution, who knows what. So simply orienting them vertically so that they can be drained, and not all positive displacement pumps will drain in this orientation. Some of them have grooves at the bottom, round sections at the bottom that will still hold up some material. But at least most of it will drain in this vertical orientation. So it is possible. Here's a concern that we have a lot about condensates or condensation on the bottom of equipment. So if that's above your product area, then you may see some condensation dripping back into your product. And we know that there's examples of where that's been a contamination problem, right? Condensate has been a source of contamination in some food products. So condensation is another issue. Now, you don't see any of this out here in the show because they have all brand new equipment, right? Brand new, nicely painted, all in pristine condition. But once it's in your plant and you've CIP'd it or you've washed it several times, this starts to happen. And do you have to mount that type of equipment right over the process system? Or can you do something to avoid contamination into the product zone if that's mounted directly above? Things like that can be an issue. Seals, static seals for valves or connections, and even bearings, right? More possible areas for concern. A lot of what we see in seal design in the center is a square groove with an O-ring in it. and it's not cleanable. There's the product right underneath that O-ring, right? It gets underneath the O-ring and it sits there and it's never cleaned out unless that product is disassembled. There's a bearing with grease. All bearings most need grease of some sort, right? It may be food contact grease, but if it's right over a hopper, then you're really going to allow that grease to drip into your food product. It's a potential source of contamination, right? That will pick up organisms from the environment, from the product, and potentially contaminate your product. Biofilms will create on crevices. That's what the one on the left is, showing some bacteria and biofilms that are difficult to clean as well. So any kind of crevice that is available for organisms or soil to accumulate in is a possible source of contamination or cross-contamination. This is talking about the mechanical seals on pumps. So a lot of what I've got here today is on closed equipment, but we have similar examples for open. If we talk about a pump, the most difficult area is many times the dynamic seal in the back of that pump. And all we need to do is make sure that the fluid gets back there during the CIP cleaning to clean that area. So anything we can do to open that up and expose that mechanical seal and the O-rings that are associated with it normally to the cleaning fluid, the better chance we have of cleaning it. And a more CIP-able design. If we look at open equipment and framework, a simple thing that can be done is that we don't want any horizontal surfaces on the framework. Can we angle those so that product doesn't hold up so that we can easily drain it when we wash it down? That's another improvement we can do in a lot of pieces of equipment. Here's an example where they did a fairly good job of hygienic design with angling the tubing so that it doesn't hold water. But you can see that it's too close. There's too close of parts in there, and you can see some buildup of soil, difficult areas to clean. How can we open up the equipment to make it accessible? So for open equipment, the key to cleaning is it accessible for someone to get to? Is it accessible for cleaning? Is it accessible for inspection? And this is an example of where tight tolerances may not make it as easy to get to. So, a possible area of concern. Here's some other areas in enclosed equipment, tanks and vessels. So if you've got a dead area, right above that spray ball, you can see a crevice up there. And if product gets up in there, that spray ball will never clean it. It will never be able to get up in that area, right? Here's some upstands on the top of a tank. Does that create a shadow zone if you've got a spray ball? Will the spray get up into that upstand and clean that or not? We'd like to see shorter upstands or get rid of them if possible on tanks and vessels. So that brings me to T-pieces in closed equipment. A lot of equipment we see has T's in it, and you need T's to install some sensors or pressure sensors, whatever. And so we recommend that any T that's off of the pipeline has a length of the T is divided by the diameter of that pipe is less than or equal to 1. So anything longer than that is going to be difficult to clean and take longer to clean and may harbor soil. So there's a couple of examples of those longer T-pieces that are difficult to clean, and hopefully this little video will show you an example of that as well. So the one on the left, you can see an L over D of 1 and how fast that area cleaned out. That's ice cream stuck into a piece of pipe. And the one on the right, you can see still going, still cleaning that dead area where the length of that dead end is just 1.5 times the diameter of the pipe. All right? So the key is easy cleanability, and long T's or dead ends are difficult to clean. Doesn't say it's impossible. 1.5 may be possible. It just may take a lot longer to get that done, right? And so that brings us to the, one of the benefits of hygienic design is less downtime, less cleaning time, and more time production. So this is a clear example of where you can get that if you improve the hygienic design. So I went through a bunch of examples of components and some factors we can consider in hygienic design. The EHEDG certifies equipment, and I'll talk about that process in a second, but there's a list of all that equipment on their website, all the components that they've certified. They also have a position paper on process connections. And I want to show you an example of our favorite process connection in the US, right? The clamp fitting, and show you how that is maybe a concern for cleanability in a CIP process. So I'll show you some of the results of that. So first I need to tell you about the test method that we use to evaluate cleanability of closed equipment like process connection. The one that I'm going to talk about most is the DOC2, the in-place cleanability test that we run and for certification. So the goal here of this document 2 testing is really to look for areas that are poor hygienic design. So it's just a screening test. It's not a validation of CIP of any component, right? It's just a screening test to look for hygienic design concern areas. So what we do is we compare the cleanability of some test item, a pump or a valve or a T or a sensor, to a straight piece of pipe. And the easiest thing to clean is a straight piece of pipe, right? So we compare the two. And we do this by removing dried milk soil from the inside surface of the devices. So we will fill a pump or a valve with soil and then try to clean it out. And we evaluate that result by looking at bacterial growth in agar that is inside that device after we clean it. And I'll show you that pictures in a second. But here's another thing I want to point out, that for me to be able to test equipment here in the US or my colleagues to test them, all the elastomers that you have in the equipment cannot be antimicrobial for the test to work properly, right? We're trying to use bacteria as an indicator, and if the bacteria are killed by the elastomer inside the equipment, then it invalidates the test. I can't really evaluate hygienic design if the elastomer is killing all my bugs, right? You'd be surprised how many times I get EPDM from suppliers in the US that has something in it, and if anyone here knows what is coming out of it that is killing sterile Thermophilus spores or preventing them to grow, I'd be curious to know. But it's supposedly just FDA approved EPDM, and something comes out of it, and you can see the purple halo there. So that agar is initially purple. When we inoculate it with spores, the spores germinate and turn it yellow, but around that gasket, it didn't let those spores germinate. And so it stayed purple. Something is coming out of that material. And we've autoclaved it, we've boiled it, we've tried everything to stop or eliminate whatever's coming out of this EPDM, and it just keeps coming. So it may be a good thing from an application point of view. If you have any bugs near a seal, it may kill them. But for the test, it causes problems. So when we have to try to find sources where there's no antimicrobial elastomer. We don't have problems with Viton or FKM, but I do see a lot of that with EPDM here in the States. And it just delays the whole certification or testing process. So this just shows you some pictures of the testing procedure. We'll fill a pump or a valve with this sour milk. In this case, we're using buttermilk. It has sterile Thermophilus spores in it. We pressurize the equipment then to 5 bars of pressure to try to get that milk in every crack and crevice within the device. And then we'll air dry it. We'll drain it out, and we'll blow dry air through that equipment to dry that milk scum on the inside surface. And then if this is some example of components that we're testing, we'll put those in a pipeline, hook them to our CIP skid, and try to clean them. So this is just a schematic of the CIP rig. We have an example of the test item here on the right. That might be the valve or the pump that we're trying to test, and then we run it through a CIP circuit. So the CIP cleaning process for this test is very mild. It's very simple. A 1-minute rinse, a 10-minute wash with a very mild detergent, and then a 1-minute rinse again. And the velocity is one of the key parameters. Whatever size pipe that is, we try to keep that flow velocity at 1.5 meters a second. That's a reference flow. And we have a back pressure of 1 bar on the outlet of the device. So after we've run this CIP, we will try to detect residual soil. So we fill the whole device with this purple auger. We fill it up, allow it to solidify, and then incubate it overnight. And then we take out the purple auger in pieces, and we try to identify where that auger turned yellow and what features of the device cause that auger to turn yellow. That yellow indicates that the Sterothermophilus spores remained in that crevice, whether it was an O-ring gasket or the inside of a pipe where there's a dead area, inside of a device with a dead area, and we look for that yellow discoloration. And so here's some examples. So there's three possible results of that test. One is that we see milk residue inside. That's a major failure because we can't even clean out the visible milk soil. So we need some changes there. Another is that we see some yellow colonies or areas, and as long as they're less than what's in the reference pipe, then we determine that that device is as easily cleanable as a straight piece of pipe, and then we can go ahead and certify it. If there's no yellow areas in the device, then it's particularly cleanable, and it's a very good design, and we can also certify it. So I don't know how well this shows up, but this is an example result of the reference pipe and the auger that came out of the reference pipe, and you can see some slight yellow areas in the picture. Those are what we're looking for, a few yellow areas in the reference pipe. That gives us something to compare to. If it was all purple in the reference pipe, then we wouldn't know whether it was cleaned after the first minute or the first 5 minutes or the first 10 minutes. So we want to have some residual there. And then on the right, you see an example of a flange fitting where the O-ring created a nice vertical yellow line from the O-ring in that flange. And that was very repeatable. That yellow spot shows up. And so that O-ring design, the groove for that O-ring is not well enough designed to be easily cleanable. And that's an example of the test result. Here's some more examples out of pump housings. Here's the cover gasket of a pump, and you can see I've circled a little bit of the yellow that came out of that groove from the cover gasket. Square grooves and round O-rings are not easily particularly cleanable. So you need a profiled groove to do a better job. Also, that O-ring needs to be exposed to the product surface to be able to access the cleaning solution, right? The cleaning solution to access the O-ring. On the right, you can see the mechanical seal area housing of a pump. And in the back of that, the front's nice and purple where the flow of the cleaning solution reached. But if you look into that groove, there's a nice yellow area around there. It's too far recessed. So there's too much of a recess there, and the bacterial spores are harbored in there. They don't get cleaned well enough. Here's an example of material on the left that came out of a mechanical seal, and you can see the yellow areas around that. Here's a pin on an idler shaft inside of a piece of a pump, and you can see the top half was yellow still, the bottom half purple, and part of it was getting clean, part of it was not. So this is just some characteristics of our test and how it can identify areas that are not particularly cleanable. Based on these results, the EHEDG has certification scheme that allows us to certify equipment components. So the class 1 is things that are designed for CIP. Class EL aseptic are things that are both cleanable and steam sterilizable and bacterial tight. So they have to go through 3 tests to be certified as EL aseptic. And then there's the EL class 2 where the equipment is designed for disassembly prior to cleaning, and ED, which is dry clean only. So there are some equipment like powder handlers and things that are only dry clean. So if you're never going to put water on them, then we can certify that they are quote unquote easily cleaned using dry processing methods. But there's no test for that. We don't have a test for that. So it's strictly a design review. We look at the design criteria and evaluate whether or not you have all the areas accessible for the dry cleaning. So let me talk a little bit about this EHEDG versus US accepted practice. And this is the dreaded, what I call the dreaded clamp process connections that we all use, we all love and use. tri-clamp type process connections. So the EHEDG says that any static seal, like a process connection, needs to have an axial stop for controlled compression so that you don't overcompress the gasket or elastomer. It needs to have a way of self-aligning the two pipes so that you don't have some misalignment, all right? And it needs to be able to expand and contract with temperature. So you can see the design there with the green check mark. That's their ideal design of an elastomer for a process connection. There's a mechanical stop where the two metal pieces come together and bottom out, and then the elastomer is next to that. There is an alignment because you have a vertical line where the two pieces have to align, right? So you always have true alignment of those pipes, and that's a good thing. What we're worried about is over-extruding of an elastomer into the pipeline, which may cause a shadow zone when you're cleaning. And here's a better picture of the problems with a clamp gasket. So it doesn't have an axial stop. With a normal rubber or elastomeric gasket, you can, if it starts to leak, you just clamp, tighten, get out the wrench and tighten the clamp tighter, right? And what you're doing is extruding that elastomer into the pipeline. And that's the picture on the left. If you don't tighten it enough, then you've got a recess where some food product may be stuck in there, and that'll be a site of potential cross-contamination where that product is never cleaned out. So ideally, you want the picture on the right? The clamp gasket is flush, and it's just the right tightness. Well, if we run this clamp gasket through our cleanability test, we get some less than optimal results. Here's an example of one with a rubber gasket, and you can see that the yellow area on the downward side or the upward side, I guess, the arrow on the pipe shows that the flow is to the right. And so you can see that there's some yellow contamination there. So the milk soil that was in that pipe that had spores in it was not adequately cleaned during CIP because of that gasket, because of that gasket protruding into the pipeline. And so that's a potential source of non-hygienic design. What the EHEDG would like to see is no recess of a gasket on a product side less than 0.2 millimeters, or a protrusion less than 0.2 millimeters. So we'll give you a little bit of leeway, plus or minus 0.2 millimeters, but that's pretty small. We always see this where clamp gaskets are not replaced enough, and so you start to see the gasket damaged. And now where does it seal at? Is there places, cracks and crevices in the gasket itself that can cause possible harborage sites for microorganisms or soil? So what are the solutions? Well, some of the solutions are costly. Switching to a clamp connection or a process connection like the DIN 11864, which has been shown to be particularly easily cleanable, but that's obviously a cost. This is another picture of DIN 11864 where we've got self-alignment of the two pieces, and we've got controlled compression of the two components, and yet the elastomer or the O-ring is exposed for cleaning. All right, so this is a fairly unique design that allows cleaning of that, and you can see the elastomer extrudes out flush to the inside pipe surface. Something like this is a better design. How can we do that with clamp gaskets? Okay, but I know we're not going to all run out and replace all of our clamp connections with a DIN 11864. We would all go bankrupt, right? Because there's too many of them. So what are some options? Well, here's one option that will get you halfway there. All right, this DuPont gasket, Calres, has a stainless steel ring on it. All right, so the stainless steel ring at least gives you controlled compression. It won't allow you to over tighten the gasket and extrude it into the pipeline. That will bottom out the stainless steel, and you can tighten the clamp as tight as you can, and it will bottom out on that stainless steel. What it does not have is it does not have a mechanism for self-alignment. So you can still have misalignment of your pipes, pipe connection and still create a crevice, okay, that's difficult to clean. In particular, because that elastomer, that CalRes, peels right off of that metal. It's not bonded to the metal, stainless steel ring. It's an improvement, but it doesn't get us all the way there. So currently, the only gasket that EHEDG approves for clamp style connections is unfortunately available by CombiFit, only available by CombiFit in the Netherlands, but they will sell to the US. And they are these, what we call T-ring seals. And the uniqueness here is that the outer part that has this T on it goes on the outside lips of the ferrule, right? So it aligns the ferrules because it captures the ferrule on each side, maintains self-alignment, and controlled compression because there's a metal, the metal groove part controls the compression, and then you have the elastomer on the inside surface. And the elastomer gives you a nice tight seal at the process side of the connection. So this is just one example of something that we use here in the US that could be improved by using a special gasket. I would like to see someone in the US make something like this or something similar. All we have to do is provide controlled compression and self-alignment or a guaranteed alignment. And then if we could do that cheap enough, then I think we can improve a lot of these process connections. Okay, so in summary, I've talked to you about hygienic design becoming more globally important in the industry, especially the European group that's going global with now these regional sections and communicating about hygienic design, how you can do it better, and training engineers really that are coming from mechanical engineering and don't know much about the food industry, how we can teach them to design that equipment that is easily cleanable, right? And so EHEDG is an advocate for hygienic design. We do have training and education programs is one of the main objectives. And like I said, we just had a workshop that we invite people in to the university to do workshops, a 3.5-day workshop on hygienic design. I've also gone to companies and done specific workshops for them and their particular applications. But I mean, my goal is really just to communicate better how you can make things more hygienic, meaning more easily cleanable, right? And easily cleanable could be easily disassembled for cleaning or doesn't require disassembly for cleaning, which means you have no cracks or crevices where water or soil or microorganisms will be trapped, all right? But the key here is that all of these design principles are useless if we have people designing equipment that doesn't follow them, where they don't follow these principles, right? So they're all useless. They're not of any help if people aren't trying to do it, trying to improve hygienic design. I realize that it's costly in some cases, but it doesn't have to be. And I realize that there's a lot of complex equipment where you've got a lot of machinery over the product area. And the thing is, can you simplify that? Can you make it easily cleanable, easily disassembled? And how can you improve that hygienic design, which will ultimately reduce your risk of a food safety issue, right? Product contamination. So I just thank you for your attendance, and I'll be glad to answer any questions if anybody has. I want to just acknowledge the EHEDG group for these slides. These are parts of the training that I took out of the slide set. They have a whole lot more materials on hygienic design, a lot of pictures, which helps a lot of the engineers see how things can be designed and what we're talking about when we talk about crevice-free and flush and easily disassembled. So I thank you for your attention. I'll be glad to answer any questions. Anybody has any? Yeah. Of course it does, yes. So here in the US, I have a lab where we will certify equipment here in the US. And people that are coming to me are saying that their customers, the buyers of their equipment are asking for certification. So it is a marketing tool for them. And because EHEDG is becoming more known globally, it is a recognized certification of something that has been evaluated for cleanability. Yeah. So it is global. Any others? I'll be glad to chat with anyone afterwards if you want. I hope this was of use, and I hope we can go out and improve the design of lots of the equipment here. Thank you.